All right, I'm just going to start if that's chill.
Yeah, go ahead.
All right, okay. So, hello everyone. I am Nathan. I also work at the tutoring center, as you know. I will be going over modules one and two, while Thomas will be going over modules three and four. And we're gonna get right into it. This is gonna mainly be overview, but there will be time for questions at the end of each of our slides, basically. So just a little overview over basically module one to two concepts. Shouldn't be too bad. So we're going to start with regular expressions. I'm not going to go too much into depth with this because it shouldn't be too complicated. You should just know the operations, right? Just keep them at the top of your head, like keep it on, you know, remember which ones are which. You have and or a clean star and then one or more or zero or one. I will give an example, but Uh, should we share these slides, Thomas, after we're done, or you think that's a good idea?
Yeah, why not?
Yeah. So, I'll just say for the operations, just remember this shouldn't be too bad. I remember correctly. We went over this in 310 and 355 as well, so these should not be too foreign of a concept for you. Perhaps the min max function is a little interesting. So, if you have a min max, you basically repeat it between one to three times. So if you have two and one with a min max of one to three, then you can have up to one to three ones basically. Overall, this should not be too difficult. I made a short example of a clock using regex, right? You have all the digits, the hours, which is zero to 0 to 19, basically. And then it also counts for 20 to 23 if you're assuming military clock. And the minutes are 0 to 59, all culminating into hours, hours, and then colon minutes. Okay, now we'll get into longest prefix matching. So just the idea of longest prefix matching is just to find the longest possible lexeme for a given token. So I give a short example here of basically the difference between a digit or a float. So for example, a digit is just one or more, sorry, an integer is just one or more digits, which is 0 to 9, 0 through 9. And a float is one or more digits followed by a decimal point followed by one or more digits, right? So if you're given an example input of 123.45 and you call get token, then some possible returns could be an integer of 123, and obviously doesn't include the decimal because at that point the integer would break, or a float of 123.45. Now, obviously, given the idea that we want to have the longest possible string, we choose 123.45, which is of type float. And you need to remember that ties, in which case the length of the lexemes for different token types are the same. Ties are broken by which ones are listed earliest. At least that's what he said in his slides. So we'll just go with that. We'll get into context-free grammars, parse trees, and derivations as well. So this is essentially the language of a grammar. So, so given a language of grammar, so, oh, sorry. Let me, you wanted hand, I'll just submit it, but, uh, so, so the language of grammar is all like W and T. So all strings W possible in the terminals T of the grammar G, given that the start symbol of the grammar can derive W in one more steps. So it's essentially saying uh, W is all possible combinations of strings that S can derive. So, sorry. And that what you should remember is that the non-terminals should be on the left-hand side, and non-terminals and terminals can be on the right-hand side. The start symbol is the first rule unless otherwise specified, and and you can see if a string is part of a language just by trying to generate it using the given grammar. So for example, here is a derivation for just BBB given a certain grammar, right? You can see that you start with A and then you try to derive BBB. So you go first, you can do A, B, and then that A can become a C, which becomes a B, and this B can become B right here, and the middle B can become an epsilon. Uh, so there's like, so this is, I believe did I choose the leftmost? Yeah, this is the leftmost derivation of BBB. There's also rightmost derivation as well. Derivations will be important for, especially when discussing ambiguity, but just no, this is just how you create a parse tree given a specific grammar and a specific string you desire. So ambiguity exists if any of the following can be written for a string in the language. So two left derivations, two right derivations, or two parse trees. Here's an example of ambiguity. In this case, G3, this grammar is ambiguous since it is possible to derive a I totally forgot the operation, but a plus, I'll just say that, which is any number of which is any number of a's greater than zero via a, b, or ba, in which case both cases b will just be epsilon. Wait, drive. Does this make sense? I really don't. Okay. Well, actually, yeah, it does. So in this case, you can have two different parse trees for any combinations of A, which means this string is ambiguous. This is an issue, especially when something that should be noted when uh, actually, yeah, no, never mind. Ignore that. Sorry, I was thinking of something else. But yeah, just know this is how ambiguity is. So now we have first and follow sets. So first sets are calculated. So basically, essentially, first sets are calculated for terminals or non-terminals or sequences of terminals and non-terminals. So terminal A is a part of the first set of Q, where Q is a non-terminal if and only if for some sequence of W of terminals and non-terminals. So basically, what this is saying is that A right here is part of Q if Q can immediately derive A in some way or form. So basically, if you if you try to generate any combination of string via Q, uh, if the first letter of that string will be in the first of Q, and two is basically essentially considering epsilon as a part of W if W can generate epsilon, if it can derive epsilon. So just nothing. So you should know these 5 rules for calculating first steps. This will, I don't know if you guys will be using the same project 2 as Bozzy's class, but historically it kind of seems like the second project will generally be related to first and follow sets. So this is also just remind, maybe you should also study up on first follow sets, how they're calculated. But we have 5 rules for the first set calculations. The first one, so as you remember, you can generate first steps for terminals, non-terminals, and not just for the non-terminals. So the first step is simply just making the first of epsilon equal to epsilon. Then the first of terminal, like you set the terminals equal to themselves for the first sets for rule 2. So you just apply rule 1 and rule 2 once. Then rule 3 is essentially saying that you add the first of B, getting minus the epsilon, because minus the epsilon to the first of A if B is immediately reachable by A. So to the leftmost, essentially. That's rule 3. Rule 4 is sort of similar, except it's saying that A2 through AK can derive epsilon. So essentially, A can reach B since A2 through AK, all these non-terminals can derive epsilon. So this means that A can generate strings that the first set of B, since you can basically say, hey, these don't exist in certain strings. So that leads to adding the first set of B minus the epsilon to first of A. And for 5, this is essentially just the rule for adding epsilon to first of A. If A2 to AK is a grammar rule and epsilon is in all of these non-terminals, or in all these non-terminal, it's always going to be non-terminal since obviously if a terminal was here, you can't add epsilon, but we're just assuming these are non-terminals. And then if they all can drive epsilon, then you can assume that first of A can also drive epsilon. So the way you would do this for a program would just to be apply rules 1 to 2, and then the rest of these rules you basically just keep looping through the first of the non-terminals until there's no change. That is how you would do it in a program. Now, follow sets, they're definitely, basically it's saying that a simple A, which is a terminal or end of file, isn't a follow set of A if and only if basically that A immediately comes, or not necessarily immediately, but A following A, this non-terminal, the symbol A can be derived, or yeah, symbol A, or it could also be end of file if it reaches the end of file. So A exists as a follow set of A if we can derive from the grammar some sequence in which A follows non-terminal A. There are also 5 rules for follow set calculation. What you should always do first is just add $sign to follow S. And in this case, follow S, we are assuming is the beginning of the grammar. So it could be something else. This is just where you enter the grammar. $sign as your, if you recall, represents the end of file. So rule 2 and 3 are kind of one thing. Rule 4 and 5 are another thing. So rule 2 essentially saying that if sorry, B is a non, so rule 2 is saying if A is a grammar and B is a non-terminal, then you add the follow set of A to follow set of B, specifically since B can reach the end of A. So you add the follow set of A to the follow set of B if you look at the right-hand side and notice that B can reach, in this case, in rule 2 specifically, if B is at the end of a grammar rule for A. Rule 3 is essentially saying the same thing, but instead of being directly to the right or to the right where the last non-terminal, you're saying that all B can be not to the rightmost, but if every non-terminal afterwards is can derive epsilon, then you can add follow A to follow B. And this is because follow A through K can derive epsilon. So essentially B has a possibility, like a string being something after A, right? We don't know. It could be C or something past this. We don't know, but that's why we have to add the follow set of A to follow set of B. Rule 4 and 5 are simpler. So rule 4 is basically saying that you can add A1 to the follow set of B if A1 is directly to the right of it. Or sorry, no, you can add the first of A1 to follow B if A1 is directly to the right of it, right? So you can, following B, you can, any string or character afterwards can belong to A1, right? And rule 5 is essentially saying the same thing, except you're saying hypothetically in between A1 through AK in this case, the A1 through AK can generate epsilon, which leads to being able to add AK1, the first set of AK1 to the follow set of B. So follow set of B afterwards can have a string, like a character that belongs to the first set of AK plus 1. And it's similar to first set of the first algorithm, basically, which is basically you apply rule 1, then you initialized each follow set to empty set, and then you basically keep iterating through to the 2 through 5 until there's no changes, essentially. Okay, so the important thing about first and follow sets is they will be important for determining whether a predictive parser or an LL1 parser can be made for a specific grammar. So here are the 2 rules that you should know. I don't know if he's going to provide you any cheat sheet or any notes during the exam or something like this, but you need to know that in order for an LL1 parser to be like, or in this case, a predictive parser, like if it can be built by, if a predictive parser will be able to run the grammar, there are two rules. So the first one is saying that for every non-terminal A and any two rules within that non-terminal A. So if non-terminal A has a different rules, you can imagine this being like so it could be alpha or beta, if like in the previous examples. But if any two rules, if any of the first sets, like if you apply intersection on that, and it doesn't equal the empty set, then you can't do it. But in order for a predictive parser to be built, basically between any two rules of non-terminal A, it always has to generate the empty set, which basically means each first set for every rule of A has to be unique, which is important because if you have ambiguity, then you'll have to do a lot more stuff to figure out whether like which rule you go into, right? And finally, the second one is it is related to the follow sets. So basically, you're trying to see if the first and follow sets are disjoint. So if a non-terminal A can derive epsilon, then the first set and false sets of A must be disjoint, right? Because this is essentially saying the same thing as one, but instead it's saying you don't know if whether you should either return or go to a specific rule. So this is, you can kind of think about how this is related to rule one. Okay. Yeah, so here's an example from the notes, I think Bazi specifically, of like a situation where you would need to determine whether a predictive parser is able to be used. So you're given this grammar. So for example, S has two different rules, A has two different rules, B has two different rules, C has two different rules, and D has one rule. You calculate the first sets for each non-terminal. Then importantly, you need to calculate the first sets for specific rules. So you need to, so you know that the first of S is A, B, C, and D, but you need to figure out what's the first of A, B, for example, in which case it's A, B, first of A, B is A, B, C, and D for rule S, right? So you can generate A, B, C, and D by going down this route. And the first of C in this case is just C, D, which can basically are the terminals that can be reached via this rule. Now, since this obviously breaks rule one, which is essentially saying the intersection of any, like between any two rules for a given non-terminal A must be the empty set in order for an LL1 parser to be built. So in this case, since the intersection of A and B, of A, B, and C are not empty, it's then the grammar has no predictive parser. Obviously, it doesn't mean there is not a parser in the first place. You could use like, I think like operator precedence is an LR parser or something. So it's not for in this case. Just remember these rules for whether a predictive parser can be built. Let's see. Now we'll get into recursive descent parsing. This was a little interesting. I don't know whether he's actually going to use unget token on the exam, given the fact that the exam uses peak, or sorry, the project specifically uses peak. But you should know these functions based on the fact that the notes went over it. And I believe the example midterm uses unget token. So get token consumes the token and returns the token as well. So that should be something you're all familiar with if you worked on the project. Unget token does the opposite of get token. It basically unconsumes the token, places back in the input. The combination of get token and unget token can be used as a pseudo peak, which most of you should hopefully be familiar with from the project, right? You have a peak function and then syntax error, right? You throw a syntax error in, which in our case exits the program. So you can obviously utilize the first and follow sets for determining how, like basically using the first and follow sets to build your parser. So the first set of rules for A, for example, determine which rule to call, right? But which is why we need them to be unique in the first place. We can't have, so we don't have no ambiguity. So you can't have ambiguity in like when determining which rule to which parse rule to call. So the follow sets are not necessarily needed with a big asterisk. So in cases where a non-terminal A can derive epsilon, the parser can you can basically just return without expanding A. Uh, so you don't necessarily need to check the follow set, since the idea is that any syntax errors should be caught when expecting next tokens later when parsing. So this is assuming you don't use an else syntax error anywhere and just return instead, right? You use like an if and then an else for the parse rules, and then you just return, because eventually the idea is that eventually those lexical errors or the syntax errors will be caught by an expect later down the line. Yeah, obviously it depends how you write your parser. So take this with you don't really need to worry too much about this section. It just you don't necessarily need the follow set for constructing predictive parsers. So here's a quick example I made for how you would basically utilize the first and follow sets when creating a recursive descent parser in this case. So you find the first sets of A, B, C, and D, as well as the follow sets, right? The end of file indicates whether it can reach end of file. So, and then importantly, similar to kind of like how in rule one, you remember rule one, you find the first set for each rule. So in this case, I'm just going to go over A specifically. So these are the rules of A, right? We have B, C, C, D, Z, epsilon, and all their first sets. And you utilize these first sets over here in determining how to build your parser. So in this case, I made it's rough pseudocode, obviously, but you get the token, which acts, so you set T equals to the token basically, and then you unget it. So you place it back. It's a pseudo peak. And then depending on what the token type is, so EG indicates you would parse BC, FH indicates you parse CD, a Z indicates you should expect the terminal Z. And in this case, since it's $, you would just return because, yeah, you look at the follow set of A, and just if it's a $, you can return. And then else syntax error. So I would highlight, based on like how like students who've come to the tutoring center, it seems like definitely study up on how to build recursive descent parser. I know the professor had like a 20-minute video on building recursive descent parsing. So I'm not fully confident on like what the exam's going to be like, since we like Thomas and I never took this class, but it seems like something that might be important. So is there any questions on modules 1 to 2 so far? Anything I could clarify or anything, I guess?
You guys should be able to unmute, or you could send it as text.
Yeah. I don't see the chat. Oh, there's the chat. Oh, there it is.
I will say, when you're doing first and follow sets, a lot of people will read that last example or that last part of the algorithm where it says like loop until changed. If you look at the notes, it'll give you kind of like a while changed loop. And the biggest mistake that students make is they loop through it and they get the first set, they populate it with like they have S's first set, A's first set, and B's first set. And then they go, well, not really much changed. I don't think this is meaningful, so I think I'm done. I'm gonna move on. And honestly, I'd say half the time you're wrong and you're forgetting something that is actually changing another first set. And that not only will cook your first set, it actually extends into your follow set, because if you notice, the follow set algorithm relies on the first set. So I would say, especially if you have time on the test, really try to make sure that when you're applying the rules, you are going until there is literally no more change. Because the misassumption, especially when you have a lot of epsilons, misassuming that you're done creating the first set can cause issues that extends multiple questions down the line. But
Oh,
otherwise, does anybody else have any questions for now?
okay. I think we're good on for module 1 to 2. It's about
Okay.
30. Okay. So I'm gonna stop sharing, Thomas, and I'll
Okay.
let you cook with your module 3 to 4.
All right. So let
How do I
me
stop?
get ready.
Right.
But anyways, guys, if you have any questions, don't um preferably don't speak over, but type a message, and if I don't see it, um
I'll remind you if there's an issue. I'll tell you if there's someone.
okay. Yeah,
Yes.
so just type messages if you have questions that you're afraid you'll forget while I'm presenting. Um so that we can kind of discuss them. So let me share my screen. All right. Can you see it, Nathan?
Yeah, I can see it.
Okay, let me bring this up. Alrighty. So this is units 3 to 4. Whoops. We're going to be discussing assignments. This is kind of where the programming languages part of the course, in terms of the semantics of things, comes into play. So we're going to be talking about types, how assigns work, how we deal with types, and what meaning we can get from like operations. So as I mentioned, we're in the kind of semantics phase of things. We started with that kind of lexical analysis, which is pretty basic. We define a set of tokens, and he mentions that it's converting bytes into tokens. This, at least for the purposes of this class, you could also kind of think of it as we're changing raw strings into tokens. So if we have a token like hi, we'll change that into the hi. Oh God, I'm not used to using this on this computer. Into a hi token and operate on that. And that's useful because it organizes things. We want to get out of using strings and bytes as soon as possible because manually iterating byte by byte or checking character by character is kind of not great. And then we get into the syntax analysis, which is our kind of parsing, and that's converting the tokens into a parse tree. That, for me, I would say I'm kind of like, well, what is a parse tree? You know, you're kind of, especially in a recursive descent parser, making a kind of tree, but I prefer to think of it as we're converting those tokens into data. So, especially if some of you have gotten a decent chunk into your project one, when we're just looking at raw strings, it's extremely hard to do operations in response to them. It's a lot easier to define a grammar, to validate it, and then convert that input into structs or data or integers, and we essentially ascribe meaning to the strings we've been given. And that way we can start doing like we can use it in our software. It's now much more usable. Um, and yeah, basically ascribing meaning to the kind of input we've been given. And the other kind of thing that syntax analysis does is it just validates that we've been given tokens. Let's validate that it matches the grammar. And grammars are useful because they limit the inputs to something that's much easier to work with than just like English. Now, after that diatribe, we're at the semantics part of thing where we're part of things where we're taking that parse tree or data and we're actually meaningfully doing stuff with it. So we first look at this kind of declaration part of thing. So or part of things. The first thing we do when we want to kind of interact and save data is to create a variable. And we've got kind of two ways to do with it. We'll expand on this later. But just keep in the back of your mind, we've got a kind of explicit way we say, hey, I want an integer. And then an implicit way where we look here and we go, okay, if this is like an int, then we're adding an int, and then, okay, we're putting an int inside of this target thing. So we're kind of parsing it out of the environment. Um, so more a kind of a separate thing is scoping, which basically asks the questions, how long is a variable usable and where is it usable? A lot of you have, or you should have interacted with scoping in some of your lower level classes. You've probably heard the term a bunch, but when we talk about it more formally, we want to set limits on the usability of variable. We don't want to waste space by having variables in memory that we'll never use again. We need some way to understand, hey, where is this variable going to be used? How do we prevent it from conflicting with things? How do we associate something like a name with memory? And that's kind of what scoping deals with. So there's a few ways of doing this. We've got block scoping, which is what most of you are probably used to. And that's where we have some kind of a block is defined by these braces, and we have like int a equals 5. And we essentially say, hey, this variable a is useful from the beginning or when it's declared to the end of the enclosing block. We'll kind of look at this more in detail later when we talk about static scoping. But he also made the exception that the static keyword makes it local to a file, or sorry, when you put it outside of a block, it's global. And if you add static, it makes it local to just a file. Global variables are kind of interesting, and we'll see how they look in a kind of full scope example. So function scoping is the other option he mentions. This is the example given is JavaScript, where he uses the var keyword, and it's important to notice that in something like C, and Nathan also mentioned to me earlier, you can kind of do this in Python. Um, in something like C, this variable x would hit the end of its scope and die. But here, we're able to still use the variable. And it basically does this by kind of finding a variable declaration and popping it up to the top of the function. So that means you could even use it here before it's even been declared. Um, and that's another form of scoping. It's a little rarer. And even in JavaScript, you can use let and const, and it will treat it kind of like a C block scoped variable. Now we have these variable names, and we kind of know behind the scenes that we're supposed to, these variables represent a place in memory. They're the name of an integer variable is the name of some list of bytes that represents an integer. And we know that conceptually, but how does the computer actually do this? And it does this using symbol tables, which are kind of, in their most simple form, it would be something like, okay, if I see the string A, and I think in your guys' project, you kind of have to interact with it, then this is actually referring to 0x100 or 1000 in hex, and it's maybe 4 bytes. So maybe some metadata too. And this is how we keep track of things. And actually, in the compiling step, we will take every instance of the A variable and just replace it with something like this, or some offset into the stack. Now, how is this organized? We have two ways of scoping things to organize this simple table. First of which is static scoping. Um, this is what you are used to, and it's also most commonly associated with block scoping. So let me check the next slide. Okay, yeah. In this example, he kind of gives this graphic over here where he kind of maps everything to a matching scope of some kind. The way I prefer to think of it is kind of like stacking boxes. So we start at our biggest box, or stacking boxes inside of each other. So we start with our biggest box, and it's just going to be our global box. And here we have X, which is an integer, and we're going to say it's equal to 0. Um, I don't know if you'll need to know this, but in C, when you see a global variable, it's declared to be 0. If you see a variable that is declared inside a block, we don't know what value it is. So we have this int x equals 0. He also mentions that these are global, and that's because when we use this name and call these functions, we can do that within any scope. But for the sake of this, I'm going to focus on the variable. So then we have this main function, and we take a smaller box and put it inside that bigger one. So now we have main, and okay, main also has an int x, which equals 10. And then we have an inner scope or an inner block. And we see, okay, we have x is a character pointer or a string, and it equals testing. And so when we refer to x here, we essentially go in this part here, we go, okay, what is x? I've got this name x, what data is it referring to? And to do this, we kind of draw a dot in whichever box we're currently in and draw it just going straight out. And this is how we check. Here it's pretty simple. We go, okay, is X in this box? It is, so we're done. But if it weren't, we would go, okay, go out to the main block box. Is X in this box? No, we're done. Or yes, then we're done. Otherwise, we keep going. Is X in this box? If it is, then we stop. Otherwise, as soon as we exit all of our boxes, this is when you'll get into an error because we didn't find our variable anywhere. Now, importantly, once we are done with this scope, I like to close the box. So let's say this printed, and it would print testing. Then we're done with this scope. We collapse it. I didn't mean to scratch this out, so this is still in play. And then we get this function call foo. Some people, based on what we did here, might think, okay, we create another box inside. No. In static scoping, especially in this kind of block scoping, when we call another function, we make a completely separate box. So I'm going to close this one. Completely separate. And this is different, and this is the main difference between static and, as we'll see, dynamic scoping. So then we've got this new box, foo. I said that like it was kind of crazy, but all right. And now we've got this character, C. And this trackpad thing is harder on my computer than my laptop. Okay, char C equals C. And then we call bar, and it continues. Bar, and I'm running out of space because I was cooking. And bar has x equals 100 int. And then we call baz, separate box. And then we print f this x. So we go, okay, what is this x I'm printfing? So we start here, and we again just go straight out. So here we would say, okay, it's not in local. So it's not, we don't look at anything in here. X is not in local. So then we look at this global scope. We see that X is 0. And if I remember correctly, you should therefore print 0. Oh, whoops. It's 10 because I forgot. That's my bad. When we do this int in main, in actuality, what we would do is we're setting X to 10. I did notice it didn't have a declaration, but we wouldn't find it in main. We'd find it in global, and it would change. So this would print 10. So that was a little kind of long-winded, but the big takeaway is whenever you call a function, you make an entirely new box separately on the outside. And once you reach the end of a right bracket or a scope, you kind of collapse it, get rid of the variables. And to search for variables, you kind of create a dot in your current scope and just search at outwards. Typically, in static scoping, this will only require checking the function you're in and checking global. Exceptions being if you're inside of a block, like if you're inside of an if statement, then you need to go outside of the block. All right. So dynamic scoping is a little weirder because you guys aren't intuitively used to it. The simple table is created and it's updated at runtime. It's constantly being tracked, and this kind of expresses itself by kind of like we mentioned earlier, we're looking at parent function calls when we're searching for things. And this is kind of like if you got continually smaller boxes and kept stacking them inside. Whereas before we had separate boxes every time we called a function. You might have seen this in Scheme because Scheme is a version of Lisp and Lisp has this type of scoping. But anyways, oh, whoops, went too far. If we look at this here, so we'll kind of set it up the same way. I got, and they kind of have the global nicely set up for us. So we have X is, and I don't like that. We have global, and we have int X, which is currently equal to 0. And then we go into main. Oh, whoops. So interesting to use on my computer. So this is main. And here we're trying to set X to 10. And we go, okay, where's X? Like before, we're doing the exact same thing. So we go up here, it's not in here. We find it here. This becomes 10. Then we have the kind of inner block, and it's kind of looking like before. So we have character pointer X equals testing. That handwriting is awesome. And then we print without an R, F. Why am I putting that? Okay, when we print, we go, okay, where's X? And like before, we go upwards and we find it immediately. So we print testing. Then the block is closed. So we go, okay. And this is cold. Then we call foo. And unlike before, I'm running out of space on my little trackpad. We build it inside of main. So, and here we got char C equals C. Then we call bar, build it inside of foo. So bar, we'll have int x equals 100. And then we will call baz, which will ask, okay, where's x? Before we got this 10 from global. Now we go, okay, it's not in here. It is in here. And so we print 100. So the main takeaway from this one is we still search the same way by going from our kind of inner box or our current box just outwards, straight outwards, exact same search. What's different is how we lay out the boxes within each other. All right. And when you're searching for variables, you're searching through the parent function calls. Now, function resolution. This is the next thing mentioned, and we kind of skipped over it before, but we have these variables with names. We're associating with a name with memory, and we have to resolve that. Well, functions also have names, and we have to have a way to figure out, okay, when I call foo, first of all, what instruction am I going to? Am I going to this one or this one or this one or this one? And then just if I know what function the function name is, okay, what if there's multiple of the same name? Is that even allowed? And kind of, I didn't really mention it. Oh, whoops. I didn't really mention it before, but when we are dealing with these resolution policies, it's language dependent, and sometimes when we talk about these kind of theoretical things, they're not perfectly represented in any language. Sometimes languages will kind of do a middle ground, but whatever it is, we have to have some way of determining, hey, when I call foo, which which one am I calling? And this one's a little easier, especially in C where we can't really declare functions inside of functions. In JavaScript you can, and that's something you don't need to know, but it's interesting. JavaScript treats functions more like variables. Um, so how do we determine which function to use when we call one? In C, we just go, okay, at least if the notes are correct, which name are we looking at? So this wouldn't be allowed. On the other hand, in C++, we go, okay, what's the name and what's the parameter types? I'm not sure if it includes return types, but I don't think it was mentioned in the notes when I looked. So these disambiguation rules, or kind of determining which foo to call, is based on the function signature, which should be at least be a little easier to understand. So now we're kind of moving on into how how different types interact with each other. So the question and kind of assignment is really core to these ideas of type. What does x equal y do? So first of all, we might say, well, it depends on what x and y are. So we have to ask, okay, what if x and y are different types? And then if we want to get more complex, what if x and y are pointers to different types? Because you might think, well, a pointer is just an address, so can't we just do that assignment easy? They're both numbers. And then you might think, well, what if we do the same thing in different languages? So in something like Python, it'll just like go, okay, I'll assign whatever y is to x and erase what was already there. And others will say, hey, what are you doing, dude? So we need to start by defining a few concepts. We need to look a little deeper as to what a variable is and what kind of how we're storing them. So the first thing we have is a name. We need names are what make variables useful. Otherwise, we would just use the raw address or use the raw offset. We can kind of abstract what's happening, the actual address. We can give it meaning, and it powers up variables in a lot of ways. So we need a name. Then we need a location. We need somewhere, some location to hold the value. Importantly, this is not necessarily the same as the address. Um, you could think of it kind of as I have a house, but the address to my house is not necessarily the same thing as my house. It just tells me where to go. It's the specific place where my house is. Um, that's kind of confusing, but it's a little bit of an important distinction to make. Then we have binding. We need some way to connect this name and location. And then we have kind of the most important thing, or one of the most important things, the value. We need an element from a set of possible values. That kind of sounds rough, but that just means we need we define a set of values. So an integer must contain a positive integer. I forget the range. It depends on what you're using, but it could be like 4 bytes. So whatever 4 bytes can represent. And so the value is just what an element from that set. So 1, -1, 0, 500. That was gross, but we're going to ignore it. Something like that. So to kind of represent this visually and help us organize, we use something called the box circle diagram, where we have the name of something, and this kind of line represents binding. The location, so Sometimes this will be labeled as like M5, M1, kind of the location of the actual object, and the value. So int x, let's assume this is global, that we put that inside the circle. The circle holds the value, or it is the value. So whatever's inside there is what the value would be. And so for this assignment, we would take the value 5 and put it inside of x's box. So we would take that value of 5, put it inside x's box. And I touched on it there, but let's see. Did I predict my next slide right? Yeah. So when we're dealing with variables and assigning one variable to another, we copy the value in the location associated with y to the location associated with x, which some people will intuitively understand, and some people I've come to understand prefer a more visual approach. And so the way I like to describe it as a secondary kind of thing is you go into y's box for this one. You go into y's box, copy what you see, so whatever's in here, and move it into x's box. And that sounds really simple now, but as you get into more complex examples, sometimes it's useful to be able to look at it through this kind of broken down way. Importantly, though, there are some things we can't assign. If you've ever done this or ever thought to done this, I'm not sure why, but intuitively you guys probably understand 5 equals x is going to throw a red line at you. You're going to get a red line and you're going to be like, oh yeah, probably shouldn't have done that. So there must be rules on what can appear on the left and right hand of the equal sign. Good rule of thumb, as we'll see, the L value must appear on the left. But to define these things, an L value simply, or not simply, an L value has a location associated with it, with the expression. And we'll kind of talk about expressions later. This usually presents itself as variables, although there are some kind of weird cases. R values is just, it just says there's a value associated with this. And as we'll see, the most common version of something like this, or not the most common, but the easiest is just if you're given x equals 5, 5 isn't anywhere in memory. You can maybe argue it's in a weird register or something. You could pull it from an immediate if you wanted to go down that route, but it's not stored in memory explicitly, conceptually. So it would be an R value. So let's move on. As I was saying, there's the reason this is useful is because it gives us multiple ways to, or it gives us the list of possible assignments. So when we got this and this, it's valid. Basically, if L is on the left-hand side, an L value, things work out because we're storing whatever value this is into the value of this box. So we need a box on the left-hand side to put the value into. So either way, we're pulling from the value here, or we're pulling it from kind of an immediate. It's looking good. Invalid is R. So this is an assignment statement and we're storing to a location. So by definition, R values don't have a location and therefore this can never work. It doesn't matter if this is an L or an R. An R, you can't assign to an R value. You can't do 5 equals, but a kind of interesting case to think about is, okay, what if you guys have probably never done this, but what if I do this? What if I do x plus y? Is that an L value? Well, x is, it's a variable. It's somewhere in memory. We've got a location. Y also is. X plus y is an R value. That's because when we do this, when we do x plus y, let's say this is 5, this is 4, we have to convert that at some point to the value 9. Now this result is not anywhere in, there's no location associated with it. So the result of this expression, I can't say anything about where it's stored. So as a result, something like this, which you intuitively may not know, may know, okay, this doesn't work. It also doesn't work explicitly when we look at it like this. So this expression is an R value. And expressions are kind of a net. They can be a variable alone. They can be an immediate alone. They could be a series of operations. They can be as complex or as simple as you want. Essentially, it's a big net that wraps around variables, usage, um, operations, the results of them. Yeah. What about pointers? So we have some unique operators for pointers. We've got the address operator, which essentially says, hey, where is the box for this? I'm giving you something. Where is this box? What's the address associated with this location? Then we've got the dereference operator. Now, these are important to look at. You guys, especially if you've taken 240 with somebody who's forced you to do like a bigger project, you guys have had to interact with these, and you probably think you know them pretty well. You may not also have, or you may have chosen not to pay attention in the lecture because of your assumption. But when you break it down to kind of a low level understanding, actually, a lot of students don't fully understand what they're doing, especially as these dereferences become more complex when you're like triple dereferencing something. So it's important to really understand these. But first, we'll take a look at the left or the L and R values as inputs and outputs of these. So we've got the address of, it must take an L value. If we try to do something like this, we'll get an error because 5 isn't in a box. It's not stored anywhere. There's no location associated with it. So if we try to get its address, we're gonna get an error. On the other hand, it returns an R value. Well, we've gotten the address of a box, but that address isn't stored anywhere. We can't do something like pretend that's an ampersand. X equals 5. Well, this is the address. Setting this equal to 5 doesn't meaningfully do anything. What we might have wanted to do is set either X to 5 or dereference X to 5. But this in and of itself, this address we get is just a raw number value. It's not stored anywhere, despite the fact that we can store it and use it later. So, on the other hand, the dereference operator, what does it take in? It can actually take in an L and an R value. So this is, you're not really likely to have used this unless you've taken like a systems course. Um, so something like this will definitely segfault. I don't know if this is syntactically correct, but it would probably segfault. But that's because it's an address that the computer is not letting you mess with. It's not because we're dereferencing an L value, or sorry, an R value. And in some like low level stuff, you'll see them dereference like an actual number, especially if they're doing like weird assembly stuff. But more commonly, you'll see it used with an L value, so like dereference X. So what does it return on the other hand? An L value. We're dereferencing an address, which brings us to a location. And that location is some kind of box. So because wherever we're going has a location associated with it, it is an L value. It has to be. There is no possibility we get an R value out of it. We can't follow something to, we can't follow a memory address and then get something that isn't stored on memory. So let's see. We've got a question. Let's see. Just to be clear, dereferencing is returning the value in the location. Not, or let me make sure I understand this. Dereferencing is returning the value in the location. E, e, Yes. I think if I understand you correctly, I think yes. And we'll talk about dereferences more here. So in declaration, this is kind of not really essential. This is not something you'd be tested on. And it's only really useful to kind of work your way through it from the bottom up. But there are a few ways to read dereferences, or yeah, dereferences. If we're declaring each time we see this clean or this star, you can kind of replace it with the words a pointer to. So we see this star once and we get a pointer to an integer. You see this star 3 times and you throw up a little bit, but it does mean a pointer to, a pointer to, a pointer to. So this times 3, an integer. On the other hand, dereferencing, each star is the location pointed to by. So if we dereference x, the location pointed to by the value of x. And then triple star, I don't really want to read that. It gets real wordy. If you want to just break it down into what type an expression is when we're dereferencing, you want to think about it as you're stealing stars from the declaration. So y is a triple int pointer. Dereference I, we've taken one of these and moved it over. So it's a double int pointer. And then we take another one, and so it's an int pointer. And finally, if we take all three, then we get to the meat of it, which is an integer. So hopefully that's a little helpful. And we've got a little, things get a little weird when we bring pointers into the box circle diagram. So we represent pointers before we just put the value in. And to some extent, there is a value, and that's just the raw address. But more conceptually, we represent them by placing the beginning of an arrow within a circle. So if we have int double pointer x, oh God, my thing got moved. Okay, x, then it's probably easier to talk about y because it's a single pointer. So if we have int pointer x, or sorry, y, this is we take the beginning of an arrow and point it to a box, and this will be an integer. And we'll work through that a little bit more. So dereference confusion. Students, as we kind of talked about, intuitively can do something like dereference x, y, but if you ask them to explain it, it's a little rough. So this is a step-by-step way of doing it, which is especially useful as things get more complex when you have more pointer or more asterisks, and it's like a triple pointer inside of like a homework question or something. So if we want to do this, dereference x equals y, we go inside of y's box and get its value. So we go here. This is the value, but what is more important is that it's this arrow. So we see dereference x. Dereference means go inside of x's box, find the arrow. So we got the arrow here and traverse it. And now we're talking about this box. So finally, we take this value that we got earlier, which is this arrow, and we put the beginning within whichever our current box is. So we traverse this, and then we went inside, put the arrow inside. So kind of as one more time, when we see that dereference operator, we go inside the box, follow the arrow. This is what we're looking at right now. Then we do the exact same thing as before. We go inside y's box, copy this value, which is an arrow, and put it inside of x's box. It would also be this value. That's tedious, and it gets more tedious, but it is, and you can come up with your own way to do it, but it is useful to have a step-by-step way to go through it that you can apply to bigger problems instead of just doing it vibes-based. So that's kind of why I had some confusion about the question. Dereferencing is returning the value in the location. It's kind of returning, or it's moving our perspective to this new box. And if we had something like, I don't know, y equals point or dereference x, our new perspective would be this box because we traversed the arrow. And so we would go as if we were looking at this box from the beginning, get whatever value is in here before copying it over to y. So hopefully that clears it up. Now we have the other side of the equation. What do we do with the address operator? So step by step, if we see it, we need an arrow to x's box. So if we see x equals address of y, we need an arrow to y's box, and we put it inside of x's, we go inside x and put the arrow there. So that would mean this goes here. They don't give us a value for y, but this is what it would look like. So this value would be kind of no longer relevant. All right. Aliases. So this brings about a kind of weird situation. So conceptually, names are just symbols associated with memory. So here we have the symbol X, and it's associated, or symbols associated with location. It's associated with this location, this M1. But what symbol is associated with this? At first glance, you might say, oh, there's no symbol associated with that. Actually, or there's no string symbol associated with that. This is another name that is associated with this location. If we give it this string, that would be associated with the location M2. And I think I've got another example. So here we have this int pointer. We're going to call it testing. We we see this equal sign, so we're putting something inside of testing circle. And it's just something we malloc. So it's an int. Whoops. And then we do testing part 2. So we have this box, testing part 2. That is way too long. All right. So now we've got this. And we do this equal sign. So we follow the process. We're setting it equal to testing. So we go inside testing. We get its value, which is an arrow, and go inside testing part 2 and put whatever value we got in there. So we have another thing, or another arrow pointing to this box. So this box has 2 ways of reaching it. We've got dereference testing, or 2 names it can be called by. Dereference testing part 2. So in this moment in time, we have an alias, which essentially says when 2 L values have the same location associated with them. And remember, we said the result of a dereference is an L value. So that usually comes about in pointers. You usually don't see that too many other places unless you do something crazy. I guess we do have this array case. I don't know that you'd be tested on this. It wasn't in your notes. It's sometimes in Bossy's notes. But because these two are 2 different names for the same location, they would technically be aliases. But that, as you can clearly see, makes things gross very quickly. So moving on, we've got kind of memory allocation and deallocation. We've got these variables. We've maybe even got locations associated with them. But when do we make that association? How do we like how do we make sure we're not wasting memory? How do we get rid of a associated an association between a name and a location to kind of eat up or prevent memory from getting eaten up? And we do that with three main kinds of ways. We've got the global kind of sector, the stack, and the heap. Global is fairly simple. It's done once. It's never deallocated. There's no reason to deallocate it. If you wanted to deallocate it, you shouldn't have made it a global. Stack allocation. This one you're intuitively used to, but it's important to look at. Um, this one deals with nested scope and function calls. So nested scope is kind of, in our blocking example, was something like this, where we had main and it had a block inside of it. Static allocation and deallocation, it's done instantly when we leave the scope. So interestingly, stack memory, if you've ever taken like 365 and paid attention to the stack pointer, stack memory is deallocated like heap memory. It's just done automatically. Alrighty. And we'll see how this kind of doesn't necessarily 100% mean that things are safety or safe. So now we have heap allocation. This one you're probably is a little easier to understand because you're used to the manual side of it. At runtime, it's done in response to inputs, and it's only allocated and deallocated as requested. Traditionally, it's malloc or no, or in C, C++, it's malloc or no, and free or delete. So this kind of heap manual allocation and deallocation, and sometimes a stack, brings about problems when it comes to pointers. So the first one we can think of is dangling reference. It's a pointer containing the value. So it's a pointer containing the value for an address of a location. So it's got to be an arrow somewhere that was allocated and then deallocated. So this box was destroyed by free. Or, as we'll see, another situation. This is a problem for a lot of reasons. One kind of example is that, well, if we forget that this was freed and we try to use it, it won't necessarily stop us because this memory is still accessible by the program, or it wouldn't have been allocated in the first place. So imagine we malloc a new struct and we start changing values using this. It could affect that new struct depending on how memory is laid out. You wouldn't need to know that, but that's one reason why this stuff is kind of dangerous is that we don't know what value it is, and it could be valid or invalid, and it can make bugs that are hard to detect. Interestingly, intuitively, it can happen on the heap. You freeze something and you forget to get rid of the pointer. So if we have like int pointer x equals malloc and then free x, right here, x is a dangling pointer right after the free. If we just do this, okay, after this point, x is no longer a dangling pointer. So it's kind of intuitive on the heap. It can also happen if you aren't careful on the stack. So I kind of had this example that I used for training one time. So we have this pointer, we have this pointer 2, pointer 3. We allocate the pointer 1, pointer 2. We set, and to kind of, I guess we can work through this a little bit. We've got pointer 1. We have pointer 2. We have pointer 3. And then we have this kind of dereference pointer 2. So we draw an arrow to here. This goes to the box for pointer 1. And then we have pointer 3, which is kind of an odd one. It's just copying an uninitialized value. But, oh, sorry. We also have this dereference pointer 1. So this goes here. And after this line, This is what things look like. Then we free pointer one. Free goes inside pointer one, follows the arrow, and just destroys whatever box it finds. So these two are obviously not dangling references. But when we go to something like this, anytime variables are declared like this, like you're used to, or they're inside of the parameters value or parameters list, they are stack variables. So when we return, we will get the address of the, or this address will be a stack variable, or stack address. The problem is at the end of this scope, so this is what the stack looks like within this scope. There's obviously stuff above it. Um, so we've got this. Oh, this is kind of corny. We're just going to put 5. And we return the address to it. So we've got this goes to here. But we get to the end of this scope. I guess it's not an L value. So we return just kind of an arrow pointing to here. We get to the end of the scope, and then the stack reclaims this value. And that's a dangling pointer as well. This memory was freed by the stack when it reached the end of this scope. Normally, you can't access this variable after you return from here from anywhere else. And that's because it's been deallocated. And so this becomes a problem. If you've ever done this and gotten weird issues and it's like worked for about 5 seconds and then not worked later, it's because later the stack got filled with another value and it overwrote what was normally there. All right. Garbage references are a little simpler. It's just you can't reach an allocated piece of memory anymore, also called a memory leak. So we have a pointer. So this is a common example. You'll see we have a pointer, which points to a pointer. And if we deallocate this middle one by using free on this, you will never be able to access this again. And if you can't access it, you can't free it. That's just hanging out. If you do this a bunch, then you have a bunch of wasted memory. I'm kind of talking for a long time. It's almost been an hour, so I'm going to speed up. Um, so yeah, there are other ways that this can happen. It's just memory that you can't access anymore through any kind of named variable. There's no path you can follow using your variables to get to the memory, and therefore you can't free it. This isn't in your notes. Or sorry, I said that too quickly. Wild pointers aren't in your notes, but sometimes they're defined for you and you're asked to find them. A wild pointer is an uninitialized pointer. So if you see something like a scope and then int pointer x, for stack variables, C does not set a default. And so this is not null like some people expect. This is just a random value. It could be null. If we're unlucky, it could be a value that would lead to a seg fault if we try to dereference it. If we're even more unlucky, it could be a value that actually works. And then we're messing with memory we did not intend to. Exceptions to this are globals are, if you're given a C environment, globals are set to null. So, or sorry, globals are always initialized to 0, and therefore global pointers will be set to null. We know where they're going. It's null. There won't be an issue. This is kind of just a quick slide. What do we do if we see A equals B? Do we copy the value, like in the case of like an integer, or do we not copy it and kind of do like a reference thing like Java? This depends on the language. The core though is just if we're copying, we're going inside the box and just getting the value and straight copying it. Whereas if we're sharing, we more bind the location to a different name. So a sharing would be like if we had x equals y, we would then have X goes to this box and Y also goes to this box. And this is sometimes useful in situations where we don't want to copy. Like if you had a 6 GB struct, you would not really want to pass by copying it. All right. I'll try and speed up through Unit 4, but for now, is there any questions? All right. If you had any questions and you're just not done typing it, send it still. I'll get to it. But for now, we're going to move on. So we got type systems. So think back to the assignment semantics slide. We asked, what does X equal Y do? And we said, well, what if they're different types? What if they're pointers to different types? We discussed how that copying works. We didn't say anything about those two questions, though. That's still a problem. We need to figure out how to deal with types. And to do that, we need to kind of think about what a type is. So when somebody says an int I, what does being an int mean? Is kind of a question we need to ask. Your first kind of inclination might be, okay, I is it's a signed number. And if you're getting crazy, you might go, yeah, on this version of Linux, it's 4 bytes. Um, that's not enough. We need more information and preferably more conceptual information. And so a type is defined as a set of values and operations. This is important, and we'll see it more and more as we go through this, that can be applied to those values. Um, a type declaration is therefore a statement that declares a variable's type. How do types interact? This is an important question. Our programs are not created using only integers. And so if there's multiple types, there's multiple interactions that can occur, especially regarding assignment, which is the focus of this slide. What do we do in a situation like this? You might say, well, X is an int, so we can cast to a float. Well, what if you're writing in a language that assumes, I don't know, that wants to explicitly make it impossible that you accidentally do like float casting, precision loss, or something like that? So depending on the situation, we may not want that to automatically work or to cast. So we have type compatibility rules, which specify when assignment operations are valid and when automatic type casting can be done. So depending on the language, the purpose of the language, when we're using certain things, these rules can be different. And they can even be different for different types. So like something like this would never fly if X was a string. So even if this worked with X as an int, it would never work as a string. Now we've got assignments covered, but how do they interact if we try to add two things together? If we try to add a number in a string and you're not in JavaScript or Python, usually something goes wrong. Uh, but for that, that is possible in JavaScript and Python. So we need a collection of rules basically to define what's possible. So type inference rules define what the resulting type of an expression is. And in this case, if we've got variables, for example, the resulting type is just the variables type. But if we've got something like this, well, if this is int and int and we're adding them, the result is an int. If it's int and float and we're in C and we're adding them, the result is probably going to be a float. So this expression's type, you can think of expression's type in this case as the resulting type. So here the whole expression is an int. X plus S is an integer typed expression. And here it's a float in C. All right. What kind of types are there? So we've got the kind of primitive set of types that we're all used to. Usually it's like an integer or a float. It's numbers, kind of characters. And then we have type constructors, which are ways for programmers to define new types. In something simple like C, you pretty much just got ints, or sorry, you've pretty much just got numbers and addresses to work with. Um, Whereas these are how we construct new types. We create a struct to gather types together. Um, we have arrays, which are a kind of collection of a certain typed element, but they are custom and they aren't predefined. Functions also, as we'll see, have a type and they can be custom. There's not a preset list of function types that you have. Like not every function is an integer returning function. We can customize these. Putting it all together, we get the definition of a type system, which is, if you're asked, it consists of the basic kind of primitive types, the constructors, how do we create new types, inference rules, and compatibility rules. So how does assignment work and how do expression interactions and operations work? What do operations do? What do they result in? Now to go back to what we were talking about, what type are functions? They map parameter types to a return types. So if we have int f takes int x float y, it takes, and if you think about the kind of abstract concept of a map, it maps an integer and a float to a resulting integer. And so functions are actually typed as maps, or conceptually. Keep in mind, and I have it on this slide, you don't want to mix up the concepts between how literally it's implemented, especially people with more systems understandings of things. So odd situations, we've got anonymous and unnamed typing. It's possible for a location to not have an explicitly named type. This is easy in the case of a struct that isn't given a name. Clearly, we have no idea what that is. And if your question is, when would you see an unnamed struct? Sometimes people will declare a struct and then just assign it to one variable. Perhaps rare, but yeah, I don't know if it's rare, but it's possible. What's more annoying is this array situation. If A is an array of ints, what type is A? Some people might say A is an array of ints. I'm not sure what the question is. Other people might say it's an address. It actually has no type. We've defined, when we say A is an array of ints, we define this expression as having a type of int. A has no conceptual type. We have no type for A. All we've said is that this expression results in an int. And you don't have to, this is something you gotta trust me. And as I say here, the implementation might be something like an address of the first element in an array in C. Do not mix up implementation in the model. The actual, you know, Linux implementation of the C language is not the same as the conceptual one. There are two different stages. The C kind of programming language is a model that has to be kind of converted into an implementation. And so even though in the implementation this is an address, in the model A has no type. Now let's return to compatibility rules. At first, you guys might have thought that something like this was obvious, or something like this is kind of intuitive, but there's actually a lot of questions that come about when we start making casting rules. Like for example, they're both explicitly the same type. That obviously should work. If they're both, or if one is an int and the other is something wildly different, like a string, that probably shouldn't work unless you're JavaScript and you just want to ruin lives. But I actually like JavaScript. Unless you're Python and you just want to ruin lives. Um, what about float x and int y? Well, then it might depend. Well, if x is on the left-hand side, maybe this works, but maybe we don't want this to work because we're making an assumption here. How often do you really want to convert a float to an integer without thinking about it? There's a lot to think about. Do I round up, down? Do I not round at all? Um, so we might have to, okay, interrogate some possibilities there. And then what if we use typedef, which is used to kind of name existing types? What if we have something like this, where we have an integer that we're calling type int height, and we assign it to an integer or an integer to it. So these don't necessarily match, even though behind the scenes they do. 2 is a valid value for inch height, but there may be situations we don't want that to work, especially in something like this. This also is an int behind the scenes, but if we set x equal to test1, which is an inch height, we might want that to fly, but in other situations, we might go, hey, I meant for this to be something completely different than this. Just because they're both numbers, I did not want that to work. So depending on the language, we get different ways to kind of lay out the compatibility rules. So we have to have a way, it boils down to how do I tell if two types are equivalent or equivalent enough that I can use assignment? There are many types. We'll discuss name equivalents, internal name equivalents, and structural equivalents. Keep in mind, though, these are all extremes. Very, very rarely do you encounter one version of these extremes, and sometimes there's even conflicting definitions. So, like for example, I can't even think of any languages that will have an issue where A being an undeclared type if it's an array of something. This having no type very rarely causes issues, but it does in name equivalents. So these are all concepts that are very rarely strictly applied. So first, name equivalents. This one is simple, but kind of odd. Types need to have literally the exact same name. This type is not the same as an integer. Or it's not name equivalent to an integer. This type is not name equivalent to an integer or a centimeter. If you try to do this, it will cause an error. The kind of exception being, well, I need to assign this to a value so I can do x equals 5. Even though this is an integer, constants of the underlying type will fly. However, we still have to consider anonymous types. So here we say these are both arrays of int, but annoyingly, A and B have no type, like we were discussing earlier. So this will not work because no type is not equivalent to no type. We have no way of knowing that. So in name equivalence, this doesn't work. To kind of address this, we have something. Oh yeah, I forgot about this case. If we name this type explicitly, then we can get around it. So that's just kind of an interesting case to keep in mind, is if we name this kind of nameless type, then something like this works, which is confusing, and it might just be up to something you trust me on. So, oh, whoops. To kind of address this, we have not really address it. It's an alternative solution. We have internal name equivalents, which is name equivalents, basically plus if they're on the same line, they're also equivalent. So we have A and B here and C, and we at first think, okay, these are all arrays. These are all unknown types. Okay, we're running into the same issue. Assignment doesn't work. This is annoying. But actually, because these were declared on the same line, A and B, this checks out. These have no type, but behind the scenes, the compiler goes, okay, they're on the same line. They're probably the same. Give it a go. On the other hand, C is not declared on the same line. So we run into the same issue where A equals C does not work because internally it goes not on the same line. I don't know if C is the same as A. I can be for sure of A and B, but not C. Structural equivalence is kind of a looser version. The problem with being more forgiving about typing is that things become way harder. So it's determined by, or harder to determine. So determined by five core rules. Rule one is that if the built-in types are equivalent, so are the types. So if we have an int and an int are equivalent because they are the same built-in type, but something like this is also equivalent because they both are behind the scenes an integer. Okay, well, how do we deal with pointers? If two types are pointers to structurally equivalent types, they too are structurally equivalent. So to answer the question of, okay, is this pointer, if these are these two pointers structurally equivalent, can I assign an inch height pointer to a speed pointer? We need to first ask, okay, is inch height structurally equivalent to speed? Now, when it comes to structs, we need to ask a few things. One, do they have the same number of fields? If they don't, you can just immediately throw it out. All right, they have the same number, let's say. In this example, they do. Now we need to ask, are they the same type? And in this example, they are not. So this is not structurally equivalent. Now, if they were, let's say this is int, we need to ask a final question. Are they in the same order? So if I had double, like high 2, and I had double high 2, I don't know what happened with that E. Because this one is the reverse order of this, even though they look pretty much the same, they are not structurally equivalent. We need them to be in the same order. Now, the arrays are equivalent if they have the same number of dimensions, the same number of entries in each dimension, and are structurally equivalent types. So in this, also, they can only be equivalent to other arrays, which is important to note. It saves time when you're actually figuring this out. So if we look at these, we see T1 and T4 are structurally equivalent. I don't suspect you'll be asked a question like this, but here it's saying this is an odd notation, but this, if we look, is 4 entries. So 2, 3, 4, 5. This is also 4 entries. So the indexes you use doesn't affect it. So the number of entries on this one is the same. The number of entries on this one is the same. It has the same number of dimensions. They're both 2D. And the types are equivalent. And so these two match. Five, functions. They need to have equivalent parameter. So if I have int, 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 if they both take 2 ints, I forgot to mention they have to have the same number. They have to have the same number of parameters. They have to be in the same order. So they have to both be int ints. I guess it would make more sense to be float. So float float or int float. They have to be in the same order and they have to have the same return value. So if this one returned void and this one returned an int, they would not be structurally equivalent. Determining structural equivalent. Basically, the plan is assume everything is structurally equivalent, loop until we are proven wrong. We're kind of running low on time. Not really running low, but I'm using up a lot of your time. So type checking prevents errors and it adds auto detection. Wait, where did those slides go? Okay. Well, basically you make a table, a 2D table, and you list every single type. So type 1, type 1, type 2. You do X's down the types that you already know, because obviously the same type will be structurally equivalent. You assume everything else is structurally equivalent. Note that you can immediately kick out arrays because arrays can only be structurally equivalent to other arrays. So if you see something like da, 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 T1 or A1, and if there was an A2, for example, then we would assume that they're structurally equivalent at the beginning, but we would not need to even consider the case of non-arrays. So we would go, okay, these are possible. And then once you have it all set up, you essentially go down the list and try to prove that things are wrong. If it's a struct, look at its fields, see if you can find out if any is non-structurally equivalent. And yeah, basically try to prove it wrong until there's nothing more you can prove. This is fairly simple. We type check to prevent errors, adds auto detection. We can do it at compile time or at runtime. Dynamic typing might be like if you return variables that could be two different types. Type safety, you can't do an operation of a value to the wrong type. Strongly typed languages enforce this. Weakly typed languages do not. Um, Now the question is, how do we determine types without declarations? Languages like Python and JavaScript do not need declarations. So how do they get away with it? Is everything just an anonymous type? That was a leading question that doesn't actually hold any relevance because in actuality, we gather information from the context and the environment instead. We put the work onto the compiler, take it off the programmer. And one way of doing this is Hindley-Milner. I always mispronounce that, but thankfully it's in big letters at the top. Um, Type checking. It's a general type inference approach. It's used in languages like OCaml, which I don't think you guys really have to interact with. It uses type and operation constraints to figure things out. We essentially need to apply constraints to kind of squeeze out the types. And so the relational operator, it must take, it looks like this. So something like A is less than B would look something like this in a kind of tree representation. So this type and this type must be the same in this kind of type checking. By making that constraint, we limit the amount of possible types, which helps us later on. So whatever these two types are, they have to be the same. And then this is, or the next part is, well, this is a relational operator. It must return a Boolean. And using that, we can say, okay, T1 is a Boolean. Arithmetic operators, here we're saying that all the types are the same. So sample midterm exam. The sample midterm exam, he mentioned that the one he assigned to you guys was for you guys to solve, and he said that he covered it in class. Unless there's a specific, if you have a specific problem on a sample midterm exam, we can cover it. Um, but I'll try to get through this. Array access, all we know is that T2 is an array of whatever type is responded by this node. And we know that this has to be an integer because it's an index. Function application, we can't really say anything about the parameters, but the type of this node is going to be the return type, and the type of the function as a whole is all of the inputs or the parameters mapped to the return type. Function evaluation. This is similar. I think did I use the wrong slide? Okay, so this essentially maps to whatever. Did I mix these two up? Okay, yeah, so this application and evaluation. Okay, by evaluation, I meant kind of declaration. And so the type of a declaration would be all of the parameters mapped to whatever the return type or whatever the expression evaluated to. And if must take a Boolean because otherwise it can't evaluate anything, or it's not an if statement. And whatever it evaluates in its expression, kind of children nodes, must be equivalent. And we deal with these kind of constraints, we combine them, and we can determine the typing of every node in the tree. And so you may have seen this kind of tree thing mentioned. Okay, I'll cover that in a second. Let's get through this quick. And we essentially take what's kind of written pseudocode and convert it into this tree. And so you see we have this array access over here. And so we can immediately, for example, determine that B is an int, and he wants it to go top down. But you could determine B is an int, C applies to whatever A is an array of, etc. Determining the types. Usually you keep a table like this. Each node has a type as you create it, and you keep track of things as you go. And then just the final thing, parameterized types. We can give a type until this is like a generics and templates. This is explicit polymorphism where it's not the same as object-oriented. Object-oriented, it's kind of the classes, subclasses thing, where we can interpret a larger class even though it has subclasses. Here, we're saying that this declared kind of operation or type can have multiple forms, and we give general behavior for those forms. Implicit, we kind of make general assumptions about the type and try to make it as general as possible. So here we have no idea what X is, we have no idea what the return type is, but we can just say these are the same type, and therefore the input of some type returns the same type. Whereas here, because we said this has to be a number, or we define this as a number, then X and Y must be numbers. And so as general as it can get is that it takes two numbers and it returns one. I'm kind of rushing through this, but okay, that's everything. So let me look. Okay, before I move on, is there any questions? I'll work through this example quickly because I did not realize how much time I was blowing. Any questions on what we just covered? All right. If not, let me find a blank slide. There should be a nice, beautiful question. There we go. I just had it. Okay. This is a fun one. All right. So we can work through this example. We have, oh, we're doing the box circle diagram. We're not doing scoping, I don't think. Okay. So we have this int pointer x. Let me try and get through this quickly. I just need the type. So we have x, which is an integer pointer, and it's at location m1. Then we go into the main function, and we have an int double pointer y. So every time we see a variable declaration, we're creating a box, which is called m2. And then we get this malloc. So we're creating an integer pointer and giving the address of it back. So we have M3, and we're giving the address of it back, which is kind of an arrow, and we're storing it into Y. So we're taking this arrow and we're going inside of Y and copying it in. Then we have a dereference of Y, but we'll talk about that later. For now, we're going to see we got a malloc again. So we've got malloc, M4, and we've got this dereference of Y. So when we dereference, for the first time ever, I'm changing colors, guys, get excited. When we dereference, we go, okay, we're at Y. We go inside Y and we find an arrow. And I scribbled a little bit, whoops. We go inside Y, we find an arrow and we follow it. And this is the box we're looking at right now. And so once we're here, malloc returns an arrow or an address, and we store that inside of our current box. And then we have x equals dereference y. So again, we go, when we see that dereference y, we go inside y, we go follow its arrow, and this is our new box. And whenever we see assignment, we go, okay, whatever value is inside here, we are going to put it inside of x's box. And so we've got another arrow. And there we go. Then we've got an inner scope, and we've got a new variable. Everybody get excited. Woo! We've got z, which we're saying is at location M5. And this is a good way to illustrate the difference between location and address. I don't know if you'd be questioned on it, but the location is just M5. The address would be the number associated with M5. All right. And then we say, okay, we get malloc. We've got M6. And we're returning an arrow, and we're putting it inside of Z. All right. Now we get Y. So for Y, we're going inside of it, and whatever we find there, which is this arrow, we're copying it, and we see the dereference of Z. So we go, okie dokie. We see dereference, and there we go. So we go inside, we follow the arrow, and this is the box we're looking at. We copy whatever is inside Y, which is an arrow, and we get this. And this is location 1. So something like this would be what should be expected. Let's see. List the set of aliases at location 1. All right, so this one's kind of weird. So we've got location M4, which right now is associated with a few things, actually. To get there, we can follow the arrow inside X, or we can follow 2 arrows inside, starting at Y, or we can follow 1 arrow, and then another arrow, and then another arrow inside Z. So M4 is getting talked to by a lot of different things right now. Then you can go, okay, what is M3 being referred to by? M3 is just being referred to by, or it's being referred to by, okay, follow the arrow starting at Y, or follow the 2 arrows starting at Z. And then we can go, okay, what about, why didn't I start at M1? M1 can only be referred to by X. And then we have M2 can only be referred to by Y. So 1, 2, 3, 4. So M5 is only referred to by Z. And M6 is only referred to by follow the arrow at Z. quiz has been muted. I'm not sure how to resolve that.
Yeah, this is something you'd have to ask the TA or professor directly. We don't know. We don't have permission to do with it, make adjustments. So
Sorry about that. Yes, shoot an email, probably to the professor. Oh, he removed the time limit, but he cannot see the questions anymore. I assume he maybe misinterpreted you and just assumed you wanted to look at the exam again, not knowing that you potentially submitted it. I think maybe you submitted it. I don't know. I would reach out to him and explain your situation again. Sorry. Does anybody else have any questions? Did this um, address, is it long fam? Anything else for now? Otherwise, I'm not sure we have anything else. I kind of doubled the length of this, but well, why M3 is double dereference? Well, okay. So if we look at, so this is Z, and to get to this box is alias or another name. It's not an alias because it's the only thing referring to it. But to get to this box, you would use this. You would invoke this. So the name associated with this piece of memory is M6. Now, if we go inside here, find the value and traverse it, then we would need to invoke the double dereference and we would traverse to this box. Does that make sense? Okay, that's good. Anything else, anybody? What's up? The explanation. So I'm not entirely certain. I would say make sure you read the question carefully. You usually are not quest with explaining first and follow. Um, but if it asks you to explain what you're doing, then I would maybe do that. Usually you're just asked what is the first and follow set, and you've the methodology is like lengthy enough that usually by getting the answer you prove you understand it. But again, we're speaking from a perspective that is not necessarily 100% sure. So just maybe double check, reread the question, make sure it's not asking you to explain. Anything else? Anybody?
well, I think that's it. I'm not seeing anything else.
Yeah. Well, whether or not there is anything else. Thank you guys for coming. Um, my apologies for making this go on a little long. Nathan was much more on the ball with regard to that, but hopefully that was helpful. Reminder, Nathan and I are, for somebody, I think some people came in a little late. Nathan and I are part of the tutoring center. We can help you with some of the concepts. The tutoring center, which is at ECG 104. Um, it's the, I forget the full name. It's basically by the intersection of like Wexler and stuff. It's by that like crepe place. I don't know.
I think that's a good
But
description. Yeah, the crepe place, honestly.
yeah. If you guys need any help with 340 projects or content, you can come on in. I'm working tomorrow and also Wednesday from 12:30 to 4. I'm not sure when your test is on Wednesday, but if you have any more questions that you weren't able to ask during this, you can come on in. Nathan's there tomorrow. When are you there tomorrow?
9 to 1.
All right.
Yeah.
So if you guys have any questions, you can come on by. I'll try my best to not speak for another 2 hours as I'm answering it, but yeah, you can. I forgot to mention that.
Yeah.
If you look up I think it's like TMS, you can hop into tutoring online. And so if you aren't able to make it to campus or you just don't want to make the drive, you can hop in during those times as well. Um, so
These,
yeah,
yeah, I think the Zoom will also be uploaded, this recording. I believe the
I'm gonna
professor
upload.
posted it.
Here, let me find the link. TMS is the name of the website. Let me stop sharing.
Yeah, TMS
Um,
is kind of the service for how people can enter and request tutoring. But I think if you just search up tutoring at it, if like Fulton tutoring, I think there will be enough information, but I don't know.
let's see.
There might be an actual link. I've never actually used it myself.
Yeah, here it is. So this is a link um, to the tutoring center. We will be posting, as Nathan said, we will be posting this. Thank you guys again. Is there anything else? All right. Good luck on your test soon, guys. Let me stop
Look, everyone.
recording.